When fuels are burnt in air, they react with oxygen to produce carbon dioxide and water. This chemical reaction is called combustion. The equation is fuel plus oxygen gives carbon dioxide and water. Energy is transferred from the fuel to the surroundings, causing a temperature rise. We can say that combustion is an exothermic reaction. It releases energy via heat.
Different fuels will release different amounts of energy. In general, the more energy a fuel releases, the more useful it is. You can compare how much energy different fuels release by carrying out a simple investigation. In this pod, we'll look at how to perform this investigation properly.
A good set of fuels to compare are the alcohols. The alcohols are a homologous series of carbon compounds. This means that they are a bit like a family in that they all share a common structure, but differ in how long their carbon chains are. The first 5 members of this homologous series are
methanol, ethanol, propanol, butanol, pentanol.
The alcohols are added into burners. These are glass containers which contain a wick dipped into the alcohol. When the wick is set alight, the alcohol will burn to produce a flame.
You can use the flame to heat a known volume of water. You can then use the temperature increase in the water, the volume of the water, and the mass of alcohol burnt to calculate the energy released per gram of alcohol.
The burner is placed under a conical flask containing 100 cubic centimeters of water. The conical flask is held in place using a clamp stand. A thermometer is held in place using another arm on the clamp stand so the temperature of the water can be measured and recorded. The thermometer should not touch the bottom of the flask. This is so an accurate measurement of the temperature of the water, not the flask itself, is recorded.
The mass of the spirit burner is recorded before being placed under the conical flask and lit. The bottom of the conical flask should not touch the wick of the spirit burner. The burner will heat the water and should be used until the temperature rises by about 40 degrees Celsius. The final temperature of the water is recorded before the flame is extinguished, and the mass of the burner is recorded again.
This is then repeated for the other alcohols. There are a lot of measurements to record, so you should design a clear results table which shows all the results clearly. It is good practice to repeat the measurements for each alcohol so repeatability can be checked, but this would take a very long time. Instead, you can compare your results with others in your class to check reproducibility.
To analyse your results, you carry out these steps. 1. Calculate the temperature rise of the water for each fuel. 2. Calculate the mass of each alcohol burnt. 3. Calculate the energy released for each alcohol using the following equation. Energy released from the alcohol per gram in joules equals the mass of water in grams multiplied by the temperature increase in degrees Celsius multiplied by 4.2. This is all divided by the mass of alcohol in grams. 4.2 is the specific heat capacity of water. Remember that 1 cubic centimetre of water has a mass of 1 gram.
Let's look at some sample results for ethanol. The temperature increase is 60.5 minus 18, which equals 42.5 degrees Celsius. The change in mass of the burner is 25.2 minus 24.4, which equals 0.8 grams. The energy released for ethanol per gram can be calculated on screen as 100 times 42.5 times 4.2 all over 0.8 is 22,312.5 joules, which is 22.3 kilojoules. So the result we get from our data is 22.3 kilojoules per gram. The actual energy content of ethanol per gram is 26.8 kilojoules. Our result is lower than this. Why?
Well, not all of the energy from the flame was transferred to the water. Some was transferred to the glass and some to the surroundings. To improve the accuracy of the result, we can make some changes to the method. It's a good idea to make sure there are no drafts in the room which could move the flame. It's also a good idea to move the flame as close as you can to the bottom of the conical flask without it touching. You could also make a heat shield to surround the equipment using cardboard-covered foil. This would reflect heat into the conical flask.